Okay, have a good break. Let's carry on. Yep, Trini, what is your answer for this one? Number 7.
Hello.
Hello.
Yes, hello, sir.
Yeah, hello. What is your answer for this one? This is an easy question. Memory work only. Before we start topic. Yeah.
Which question, sir?
Number 7 just now. You were asking. I told you I forgotten about the question. Focus 15. Which of the following is true of the internal resistance of voltmeter and ammeter? Memory work.
Boy.
Okay, good. Voltmeter always has what I call infinite resistance or high resistance. Ammeter is very low. Usually we call it 0. Okay, let's start a new topic then. Good. Make sure you continue to do the focus. No shortcut one. Especially your STPM. It's a mainly calculation problem.
This SPM
SPM is simpler. STPM is different. STPM are much higher. You go to university, even worse. Right? University even more demanding. Cannot expect you to be always like a small child. You have to start growing up. And one day you have to start to work already and then get married and settle down and start to have your children. That's what responsibility is all about. Okay, we are going to cover magnetic field today. Probably concept of magnetic field. And then force on moving charge. We'll try to cover these two topics if we can. And then later on, 13.3 force on current carrying conductor. Magnetic field due to current. Force between two current carrying conductor. Right? This is the force of the conductor carry a current in the magnetic field. This one is the two conductor together. Because the conductor itself, right, whether it's a solenoid, will contribute to magnetic field. And then finally, we study determination of ratio of E over M. Okay, so these are the new things you need to remember. This is the old one. You need to find where is your electronic charge and not, right? Permeability of free space for magnetism. For electricity, you use permittivity. As your magnetic field syllabus. Always refer to syllabus, even though it's not much. The other thing you need to prefer is your past year paper, right? Because these two is important to tell you how much you have to study. Without these two, your syllabus is very bad. Not enough information. You don't know how much you want to teach. Right? Concept of magnetic field.
You say which two?
Your past year paper.
Oh, I mean this learning outcome and the past year paper.
Learning outcome is very big. It tell you explain magnetic field as a field of force produced by current carrying conductor or by permanent magnet. That's all. So you don't know how wide they want you to cover. So that's why you have to go to past year paper and work through, then you realize how much depth they want. Just like if you go to last topic, you say Kirchhoff's law. So Kirchhoff's law, then you have to ask yourself, is resistor in series and resistor in parallel in the syllabus or not? Right? Not mentioned there. So you have to go to past year paper and see, and you realize, yeah, resistor in series and resistor in parallel is in the syllabus, even though it's not mentioned. And force on moving charge, right? This formula, this is a vector formula. And then use this equation. And then define your B. Describe the motion of charged particle parallel and perpendicular to uniform magnetic field. A lot of uses. Magnetic field is widely used, right, in lifting heavy car to the junkyard, so that you can scrap out what is useful, what is not useful. Loudspeaker, where you loudspeaker to convert electrical energy to sound energy. right? Your voice coming out cause this vibration and it produce sound energy. And then the first thing you have to determine the charge and the mass of a charged particle. So first thing you have to know how the charge of the particle, the charge of the electron. This one we use Millikan's experiment, right? Under electric field. Then we use electric and magnetic field to select the velocity of a particle. That's what we will study later on, so that we can find the charge to mass ratio. Right? Where's the users? Right? Magnetic resonance imaging. Okay, so not much about application in your STPM. Right? Sometimes it looks so dry lah. You see as if there's no application, but there is application. Even the electric train, levitating train, right? They can either use repulsion or attractive force, so that the train is moving on a cushion of air. Okay, let's go to concept of magnetic field. Magnetic field is an example of a field of force, or force field. Right? Few lines of current carrying conductor using iron filing. Right? We can turn on the current in the long wire. Then we sprinkle iron filing on the cardboard there. And then tap the cardboard, then you will see some pattern there. Same like the magnet there. Right? You put cardboard there on top of the magnet, sprinkle iron filing, tap the iron filing, then you will see this pattern. Right? There must be some force trying to push a small, tiny iron filing to the position of the field. So the thing you need to introduce is magnetic field is produced by current carrying conductor or by permanent magnet. Here is current carrying conductor, produce magnetic field. There's your permanent magnet. Two things. Right? That's your SPM work for magnet. You need to remember there's no individual magnetic pole. Right? We got positive, negative charge. So you can separate them, but magnet, we don't have separate one. We have two together. Right? Electric charge, we can separate them. Magnet cannot. Magnet, we have both pole together, north pole and south pole. Then we have north pole and south pole, or south pole and north pole facing each other. There will be attraction, or we call it light pole attract. Sorry, and light pole attract. And light pole repel. Same pole, north and north, or south and south, they repel.
Yeah, they repel.
Okay.
Hey, Chair, what do they mean by charges can be separated but magnetic pole always come in pair?
So you can have a you can have a positive charge, can have a negative charge separately.
Yes.
But here you cannot cut the magnet to north and south pole. Right? They are both together. The north and south pole exist together. You cut the magnet, you still be a south pole here and a north pole here. That's what I mean. You cannot separate them.
Understood.
Okay, there's your SPM work. We have a
Which
magnet.
means there will be a north and south. It cannot be a north.
It's always together. Cannot separate them like positive and negative charge. You cannot separate them like that.
Okay.
Right? We can use iron filing. Right? Iron filing is made of metal, tiny metal. And we tap the table, small table, and you will see the fine lines there, showing that there's some invisible magnetic force acting on the iron filing. Or we can use magnetic compass to trace a few lines. Okay, this is just a review of your SPM work, magnetic field lines or line of magnetic force of a bar magnet. Right? You always start from the north. That's our choice. North to south. Lines never intersect, never cut each other. Right? Where it's close to the magnet there, we take the area around here. We will find the concentration of line is a lot passing through the area. So we have a strong field. Right? The line basically it's just imaginary. It describes the way the field behaves as well. And then this part, this area there, you can see very few lines passing through the area compared to here. So it's weaker field. Right? Imaginary. It doesn't exist. We just think on it. You can just illustrate by iron filing. And then if you want to know at this point where the direction of the field, then we just put a magnet arrow or compass there. Then it's a tangent to the curve there. Follow this arrow. Right? It's going to point to the south. Okay with that?
Good answer.
So uniform field, the lines are parallel and evenly spaced.
Sure, the low concentration of field line, the one very far away, right?
Far away also, low concentration.
Yeah, the one far,
The
one
side one also the
strong
same. Where there is more lines per unit area, then it's stronger field.
Sure, the direction of the field or the point, their imaginary line, they are just trying to say where
it's in our head only. We can't see it. It's in our head. We imagine it. But for magnetic field, we can illustrate it like using compass to draw it out. Or we can use iron filing. No? That means the only way to see it is to put iron filing. No? We cannot see it. That's why it's called imaginary. Yep, in our head, Okay?
But the arrow is coming out from the north, but it's going through the south.
That's our choice. Right? We use the north pole.
Oh, you can also use the south lah.
I can use the south. It depends on your choice. But this is determined by the scientist, not by you. Right? It's the north pole. That's our choice.
So this is just hypothetical lah.
That is our choice. So you have to remember that. No?
Okay.
Scientist choice. Just like we choose from the field will start from positive charge to negative charge. And how to determine the field, direction of field, we use a positive charge as our guide. How do we test the presence of magnetic field? Yeah. How do you test the presence of magnetic field? Your STPM work? How do you know magnetic field is present?
Put a magnet lah.
Yeah, you can either put a magnet hanging in the air there. If there's a field there, it will swing. And then you align with the field, Earth magnetic field. Or right here, can use current carrying conductor, place a magnetic field, turn the current on, it will be deflected. If you put larger current, deflected more. Right? So magnetic field will produce a force on a suspended magnet, as a suspended magnet, or current carrying conductor. We can use two ways, either a tiny magnet, suspended, or the force on a current carrying conductor to test the presence of magnetic field. Okay, current carrying conductor will be deflected. That's our one of the topic you study. So what is magnetic field? Region of space, just like a football field, region of space, but where a force is experienced by a current carrying conductor. How do you know the field is there? We put a current carrying conductor there, it will be deflected, or we put a permanent magnet to test it. Two things, either a permanent magnet will be deflected, or a current carrying conductor will experience a force in the field. That's how we know a magnetic field is present. Okay, example, show the direction of the field at P and Q. There's your P, there's your Q. Yeah. Can?
Show the direction of magnetic field.
P and Q.
P and Q. It is going. The Q is going towards south. P is going. It's like not facing north.
Right? It's tangent.
P and Q are facing south lah.
Like that. Follow this arrow. but it must be a tangent at this point, right? Tangent at this point. Okay.
I mean, P and Q, they go to south, right? Anyway.
Okay or not?
So
Just
P and Q,
touching,
they go south, right?
just touching a tangent to the curve here.
No, do they go south or not?
It's going south over there, pointing south.
Okay.
This one is
T
pointing
also,
south
right?
also.
Yeah.
Right? But the straight line is a curve, is a tangent. How about this one? Why does it? Why does the field never cross?
Field never cross.
Why does the field never cross?
I mean, they don't intersect, lah.
Yeah, why?
Why?
Why they don't intersect?
They are two different magnetic field, lah.
Think through. Why they don't intersect? Okay, there's a two field, north and north. Right? They will look like they are going to intersect. Even if you look at this point there, it looks like it's going to intersect, but the key to remember is at that point there, it will be going that way. For this one, it will be going the other way. Right? It looks like they are intersecting, but remember that the field is a vector field, so we add the two vectors, we get a resultant. So they don't intersect. They will interact to get a resultant. That's the key important thing. Magnetic field is a vector field. At the point where the two fields appear to cross, the vectors act to give a resultant field. That's why they never cross. So that's why we draw it this way. Can? Yes or no? Okay. Okay, we completed magnetic field, giving us an idea.
Wait. So the reason is because the magnetic field interact to give a resultant field. That's
the vector field. So the two vectors interact to give a resultant field. So they never will cross like this one. Right? That's a resultant field. They will never cross. They repel each other or north to north.
Okay. Just because they want to give resultant, okay.
Okay, they won't cross because the two are vector. The two vectors will add to give a resultant. So they are all like repelling each other, going north there.
Yeah.
Right? Like here. Right? Repel. You won't see them crossing. That's the resultant. That's why they are going that way, straight up or straight down. Okay, next topic. That's why we are learning magnetic field region of space where a force is experienced by a current carrying conductor or opponent magnet. That's how we detect the field. Then 16.2, force on moving charge. Right? How to represent the field? Right? Your arrow, the head, that's the tail. Right? We are only interested in uniform field. So how do we show that? Parallel line, equal distance apart. Parallel field, uniform field, and in 2 dimensions. Right? We look at the arrow tail, then we see a cross there. This is going into the page. Right? This is the tip of the arrow coming out. That's why we see the dot there. Right? This is coming out of the page. Right? Sometimes they may draw for you 3 dimensions. Right? There's a field you must be able to read. It's going in. Right? We introduce a new term, B, for the field. Right? It's called magnetic flux density or magnetic field strength. Americans tend to call it magnetic field, but it's a vector quantity. And there's a moving charge there, positive charge. Right? Moving to the, well, you can call it to the right if B is going in. And there's a force going up on the charge there if it's moving this way. So we can either call this one going in, represent this way. Right? There's a positive charge. There's a force. There's a V. right? Either look it in 3 dimension or 2 dimension. Magnetic force on moving charge. Same, there's a positive charge there. The direction of the field going in. Right? Moving charge with a speed, velocity v. So this is always a perpendicular component times q times v. Right? In this case, the perpendicular component is your b. Right? We are looking at the maximum field, maximum force. These two must be perpendicular, the field and the velocity, where b is the perpendicular component of p to the velocity. Right? We call it magnetic flux density or magnetic field strength. Then you have the force. Magnetic force on moving charge. Right? B is basically measuring the strength of the magnetic field, how strong. That's why some older book will call it intensity. So if the charge is moving perpendicular to the field, then the force is maximum. That's why we just write VQV. Right? Remember V, that B there is a vector quantity. That velocity is also a vector quantity. Is the velocity of the moving charge. And Q is the charge. Is this charge there? Right? So if the charge is not moving, it's not moving to the right, it's moving at an angle theta, then we use our BQV. That means we take the component of V perpendicular to B. Make this component, just put it to B, which is V sine theta. Right? So that gives you a magnitude. Okay. Use this component and see get the force. Okay, direction. We can use direction. Fleming's left-hand rule. Right, the thumb represent the motion. The first finger, the 3 fingers must be perpendicular to each other. Right, there's the thumb there, the force, the motion, and then there's the first finger. Right, they're 2 perpendicular to each other.
Wait, so the 3 fingers has to be perpendicular to each other?
Yes, perpendicular to each other.
Okay.
Right, the 3 fingers are perpendicular. This is your force. This is your field. And then this one, sorry. This one is the current. Okay. Traditionally, right, so the Fleming's left-hand rule gives the force on a charge moving with perpendicular magnetic field. The thumb, that's our traditional way. Right? Thumb is the motion. First finger, the F for field. Second finger, C for current. But as I say, students are very imaginative these days. Can use whatever method to help you. Right? Just like my student in Murphy teach me to use this one. McDonald's fried chicken. Yeah, you can use that. McDonald's fried chicken, motion, field, current. Right? Up to you to use. Or father, mother, or mother, father, children. Whichever can help you. Right? And then remember, your current is the rate of flow of positive charge. That means the current is the direction of motion of positive charge. Right? It's mnemonic. Okay, so that one summarized for you. Velocity and angle, the same thing. Thumb, first finger, second finger, all mutually perpendicular to each other. Current is the rate of positive charge. Let's remember that. That's the velocity of the charge direction. So if that's your field to the right, that's the velocity there. Right? Where's the direction of the force? Yep. Use your finger. That's your field.
The force is the first finger lah.
Yeah, where's the direction of the force?
Thumb.
That's your field. That's your velocity. Even though it's an angle, doesn't matter, put it perpendicular. So it's, where is it? Up, down, left, right, in, out. That's the force. Yeah? That's the force. That's your field. The field. That's your velocity. That's the force. Coming out,
Force
isn't
is
it?
the thumb lah.
Yeah, the thumb. So you should coming out. Oh. Right? Magnitude wise, we can either use a perpendicular component to velocity, which is that way there. Right? That's why we get that. Either way, either component of velocity perpendicular to the field, which is here, the same thing. Right? Same answer. So the direction of force is out of page. Ken, your SPM work. Can or not? Can or not?
Can.
Okay. Right? Make sure you know how to do that. We will try some example later. Okay, we can, instead of remembering all the Fleming's rule, left hand rule, right hand rule, so many rule, right? We use vector easier. That's why we write as a vector. F equals to QV times B. Right? This is a vector product. And where there's a vector product is VB sine theta. It's called a vector product or cross product. The order is important. That means you write your V first times your B, not B times your V. V times your B is a vector product or cross product. Direction of force, we use our right hand. Right? Use our right hand. Yeah, right hand there. That one we move from our V. Right? Motion is from V to B. And then the thumb will give our direction of the force. If you want to use it that way. Right? Because in science there's so many rules there. It's better to use a vector representation, and then that's faster. One rule only. Thumb give direction of the force. Right? This is a case for positive charge only. So if the charge is negative, where would it go? Where's the direction of the force if the charge is negative?
Negative.
Yeah. If that charge there, that motion there is negative charge, where would the force be?
Down. The force will be down.
Yeah, down. Because our velocity is now going, the motion of positive charge is going that way now, to the right.
Because they say it's always positive, then it will go up.
So go like that. Oh. Okay, go like that. Oh. Okay, good. Right, through the positive charge is moving in the opposite direction.
Yeah, opposite lah.
Okay, now.
Okay.
Okay, let's test you, see your understanding of this formula.
Okay.
When the charge is stationary, what happened? You put a stationary charge in a magnetic field, what would happen? Your V is 0. Yeah, V is 0.
Oh, yeah, V is 0.
So what is the force?
There's no force lah.
So what happened to the charge?
Remain constant.
Okay, we have to stop in a while. Right? V equals 0.
Yes.
F equals to 0. Right? Charge remains stationary, doesn't move. Charge moving parallel or anti-parallel to the field. That means at 0 degrees or 180 degrees? What happened to the force?
The force does not change.
But the force doesn't change. Theta is 0 or 180. This is F is 0. Right? That
The
means
force is 0 lah.
if the angle is 0, then it moves parallel. It continues to move with uniform velocity. It doesn't change direction. Yeah? Can.
Can.
If it's perpendicular to the field. If the charge is moving perpendicular to the field, what will happen?
Perpendicular.
Perpendicular to the field.
So sine 90.
It means left-hand rule. Right? You got a maximum force, and the force is maximum
perpendicular.
and perpendicular to the velocity and b. Yeah? Perpendicular to velocity and b. Right? Fleming's left-hand rule. What happens if it's a moving negative charge?
The force is in opposite direction.
You just treat as a charge, a current moving in opposite direction, and then apply Fleming's left-hand rule. Okay, from this equation, right? You read different book will tell you differently lah, but you must follow your syllabus lah. Right? Syllabus definition is from this equation. Right? We put theta equals 90 degrees, then we get BQV. Then we subject our B, take the QV down. Right? Then we can see we call B 1 Tesla, where the force is 1 Newton, the charge is 1 Coulomb, and velocity is 1 meter per second. Right? So we define our magnetic flux density B is the force on a unit charge moving with a unit velocity perpendicular to the field. That means B equals to F if Q is 1, V is 1. Same definition for Tesla. Unit of magnetic flux density when the charge is 1 Coulomb, velocity is 1 meter per second, and the two must be perpendicular to each other. That means the V and the B must be perpendicular to each other. Okay, then the force is 1 Newton. That means F is 1, Q is 1, V is 1, then your B is 1 Tesla. Oh, that's the alternative unit for Tesla. Okay with that? Any question?
No.
Yeah.
Wait, answer.
We are finishing soon.
Okay.
Definition, nothing much, just memory work. Okay, motion of charge in magnetic field. Magnetic field is right out of the page. That's the motion of positive charge. Move perpendicular to the field. Where's the direction of the force? Where's the direction of the force? Yeah, Ken? There's a field. Sorry. There's your current direction. Your field is coming out. That one there is your current or direction of the positive charge. Direction of positive charge is this one. This one. That one is going in. This one. Going in. Coming out, sorry. Coming out. And that's the direction of the force. So where's the direction of the force? Play means left hand rule.
Upwards.
No, how to be upwards, downwards. Okay,
Oh.
that's your current. That one is coming out. One down. Yeah, that one. Not going in, coming out. That's your field. That's your force is downwards. Okay now. Magnitude.
Wait, why downwards, sir?
Play means left hand rule. Okay, I show you already. There's your field coming out. There's your current. There's a moving charge there. That one coming out. There's your thumb there. Going down. Yeah, use your hand. Use your left hand rule, not right hand rule. Left hand rule. Yeah. That one like that. So it's to the right. This one is coming out. First finger is coming out. Can or not? Yeah, magnitude is BQV. Go back and think through it. We'll go over it next week. If it's next period, if you still have problem sorting it out, there's a lot of question there. This is your SPM work. We are just revising, that's all. So I'll stop here. Make sure you prepare for your test.
Just to be sure, test from chapter 1 to chapter 4 only, right?
Chapter 12, chapter 13, chapter 14.
Chapter 15?
1 to 3.
Oh, I thought 1 to 4. Okay. Thank you.
1 to 3 only.
Oh, okay.
Electrostatic, capacitance, electric current.
Yes. Okay.
Okay. Have a good day. I see you on Friday for the
Good day,
test.
future. Okay. Finish already, sir?
Finish already. Time is up already.
Oh.
The Zoom is 40, 40, 40.
40. Okay. Okay, thank you, sir.
Okay, bye-bye.
Bye-bye.